Hello guys, welcome to the second episode of the Photography Beginner Guide. In this episode, we will talk about the challenges of making a wide-angle lens. Every camera lens is actually a convex lens. It converges light to form an image on the camera sensor. With short focal length, an image could be formed in front of the sensor, which will look blurry. To solve this problem, lens designers need to make the image move further so that it could land on the sensor while keeping the short focal length and thus the wide angle of view. The magic component to be added is a concave lens. When putting in front of a convex lens, it will diverge the light first and make the image to be formed further away from the lens. So yeah, the big bob-shaped front element that you see on an ultra-wide-angle lens is usually a concave lens. I know you may wonder, the bob-shaped glass looked exactly like a convex lens. How could it be a concave lens? To determine how a lens would bend the light, we will need to examine the thickness of its center and its edges. If the center is thicker than the edges, it will converge light. That makes it a convex lens. On the other hand, if the edges is thicker than the center, the lens will diverge light and thus be defined as a concave lens. Let's take a closer look at a wide-angle lens. From the lens structure diagram, you can see that the edge of the front element is thicker than the center part. Therefore, despite its bob shape, it is undoubtedly a concave lens. Using such a big bob-shaped glass at the front is not for showing off. The shorter the focal length, the higher the dielectric power needed for the front element to diverge light. Dielectric power may sound like a fancy term to you, but it just means the power to bend light. High dielectric power could be achieved by large curvature. That's why the front glass of wide-angle lenses is always in bob shape. Large curvature bob-shaped glasses require precise craftsmanship to make. This is the first challenge to produce a wide-angle lens. The second challenge is chromatic aberrations. Using a concave plus convex lens structure would accumulate chromatic aberration, causing some weird color fringes at sharp edges in the photo. To minimize this effect, low dispersion glasses and doublet lenses effectively work together to compress the chromatic aberration. The third challenge is distortion. In an ideal situation, every single spot on an image plane should have the same magnification as the object plane, meaning there's no distortion between the object and its image. However, in a real-world situation, magnification would hardly be the same on every spot on an image plane, causing distortion to occur. There are two types of distortion. If the magnification on the image plane decreases when moving away from the center, the magnification at the corners will be smaller than on edges, since it is further away. This will cause barrel distortion, which usually occurs in wide-angle lenses. On the other hand, if the magnification increases as it moves towards the corners, pincushion distortion will occur. This is commonly found in telephoto lenses. To correct barrel distortion, a spherical lens is introduced to high-quality ultra-wide-angle lenses. Unlike ordinary spherical lenses which have fixed curvature, a spherical lens can have various curvatures. Its shape can be customly made to fit the design needs, like to correct distortion. However, aspherical lenses are much harder to manufacture and their cost is much higher than spherical lenses. Also, their error tolerance level is very low, meaning any imperfections in manufacturing or assembling will greatly reduce the image quality. Another key to reduce distortion is the design of focus mechanism. Autofocusing lenses usually have one group of moving glass to adjust the focus in order to reduce the workload of the AF motor. The disadvantage of this design is there is no offset to lens aberrations while the lens element moves, causing distortion to occur. A manual focusing lens needs not to worry about the workload of the AF motor. Therefore, a more balanced design can be used. Two lens groups will move in opposite direction while focusing, minimizing distortion to almost zero throughout the focusing range. We hope you enjoyed this episode. More is coming up, so make sure to subscribe. We'll see you next time.